In this lecture, I want to look at a second fundamental contribution of Condorcet, namely the Condorcet jury theorem. Condorcet had this idea that the object of government is to make decisions that are in the best interest of society. And this naturally leads to the question, which of the voting methods are most likely to yield the good outcomes? Now, implicit in this question is the idea that there's some outcome that is objectively identified as the good outcome. And this is the setting for the Condorcet jury theorem. There's some proposition, and we're trying to determine, or the group of people is trying to determine whether or not that proposition is true or false. And there's some objective fact of the matter about whether or not A really is true or false. So for example, a jury in some courtroom is trying to determine whether or not the defendant is guilty or innocent. And there's some fact of the matter, the defendant really did the crime or really didn't do the crime, and it's the jury's job to somehow get together and determine whether or not the defendant is guilty or innocent. Now we're going to assume that each voter has a probability P sub I of correctly identifying whether or not A is true or false. So what that means is if A is true, then voter I has a probability of P sub I of reporting that A is true or voting for A being true. And if A is false, then voter I has the probability P sub I of reporting that A is false, or voting for A being false. So P sub I is the probability for voter I of being correct. And we're going to assume that everybody is minimally competent, where minimally competent just means you have a probability, each voter has a probability of greater than a half of getting the answer correct. Of course, if everybody has the probability of exactly a half of getting the answer correct, that's just like flipping a coin, flipping a fair coin to determine whether or not the answer is correct or not, or whether or not A is true or false. So we're going to assume all of the voters are minimally competent. Now, let F be a group decision-making method. So the idea is we're interested in whether or not the proposition A is true or false. All the voters get together. They report their opinions about whether A is true or false, and we need to somehow aggregate all of those opinions. Now, let pi of FP be the probability of getting the answer correct given the skills of each of the individuals. So given the probability for each individual of getting the answer correct, and some way of aggregating everybody's opinions about the proposition A, we can ask, what's the probability that that group decision-making method will actually get the answer correct? So let's look at an example. We'll look at an example of two group aggregation methods. For concreteness, let's assume that there are three voters, and they each have the exact same probability P of getting the answer, of correctly determining the truth or falsity of the proposition at hand, proposition A. Of course, I'm assuming here that all the voters have the exact same probability of getting the answer correct. This is an idealization which we can easily drop, but to make our calculations simpler, let's just make that assumption. Now, one rule we could employ is the expert rule. You identify one person as being an expert and just ask that person, is the proposition true or false? And you go with whatever answer that person says. So, of course, in this setting, the probability of getting the answer correct using the expert rule is just going to be P. It's just going to be the probability that the expert you choose actually gets the answer correct. Now, a second rule we could use is majority rule. Majority rule asks everybody to vote on the proposition. So you say either the proposition is true or the proposition is false. And then you go along with whatever the majority says. So in this case, if two people say the proposition is true, then the output of the majority group decision-making method is that the proposition is true. If two people say it's false, then the output is that it is false. So again, we have just three voters, and we can ask, what is the probability that by using majority rule that you'll get the answer correct? Well, let's see. It's going to be the probability that everybody gets the answer correct, which is going to be p to the third power. So why is that? Well, we have 3 voters, voters 1, 2, and 3. What's the probability that voter 1 gets the answer correct? Well, p. What's the probability that 2 gets the answer correct? P. And what's the probability that 3 gets the answer correct? That's also p. And so we're going to assume that whether or not a voter gets the answer correct or not is independent of whether or not of the abilities of the other voters. If that's the case, then the overall probability that everybody gets the answer correct is going to be p times p times p, which is p cubed, plus the probability that at least 2 people get the answer correct. So there are 3 ways in which 2 people could get the answer correct, namely voter 1 and 2 could get the answer correct, voters 2 and 3 could get the answer correct, and voters 1 and 3 could get the answer correct. So this is a situation in which one of the voters gets the answer wrong and everybody else gets the answers correct. So you can ask, what's the probability of that situation? Well, it's going to be the probability that a voter gets the answer correct times the probability that a voter gets the answer correct times the probability that a voter gets the answer wrong, which is going to be p times 1 minus p. Because with probability 1 minus p, you'll get the answer wrong. So the probability that a majority gets the answer correct is going to be p cubed plus 3p squared times 1 minus p. And here's a simple theorem. When there are exactly 3 voters, each with the same probability of getting the answer correct, of choosing correctly, then majority rule is preferred to the expert rule. So what does that mean? Well, that means that the probability that the majority rule gets the answer correct is going to be greater than or equal to the probability that the expert rule gets the answer correct. And a simple algebraic calculation will verify this result. So remember that the probability that the majority gets the answer correct is going to be p cubed plus 3p squared times 1 minus p. And I want to prove that that's greater than or equal to the probability of the expert rule getting the answer correct. So that's greater than or equal to p. Well, let's just, to verify that, let's prove that p cubed plus 3p squared times 1 minus p is actually greater than or equal to 0. So in order to see that, we just need to do a little bit of algebra. Note that p cubed plus 3p squared times 1 minus p, this is equal to p times p squared plus 3p minus 3p squared minus 1, which is equal to p times minus 2p squared plus 3p minus 1, which is going to be equal to, just factoring, this is going to be 2p minus 1 times minus p plus 1. So all I have to do is verify that this product is greater than or equal to 0. Now, why is that true? Well, that follows because p is greater than or equal to 0, because p is a probability measure, but p is also less than or equal to 1. Since p is less than or, so this component is greater than or equal to 0. Minus p plus 1 is greater than or equal to 0 because p has to be smaller than 1, smaller than or equal to 1, because p is a probability measure. Also, remember that p must be greater than 1/2. If p is greater than 1/2, then 2p minus 1 has to be greater than or equal to 0. Why is that? Well, 2p has to be greater than 1, so 2p minus 1 has to be greater than 0. So since each of these parts of the product, each of these components of the product or factors in the product are greater than or equal to 0, the product of these numbers is greater than or equal to 0. So we're able to verify that the majority rule has a probability of getting the answer correct that's at least as high as the expert rule of getting the answer correct. Now, if we assume that our voters have different probability measures, we can also prove that majority rule is preferred to the expert rule. The calculation is a bit more complicated, but it's still relatively straightforward. Well, we're about ready to set up and state the Condorcet jury theorem. Now, in order to understand the Condorcet jury theorem, we have to understand how to answer the question, what is the probability that at least m voters are correct? So we have a population of n voters, and we want to know what exactly is the probability that at least m of them are correct. Well, the way we calculate that probability is we consider the situation when exactly m voters are correct, plus the probability of the situation in which exactly m plus 1 of the voters are correct, plus the probability of the situation in which exactly m plus 2 are correct, plus all the way up to the situation in which everybody is correct. So given m voters, so suppose h is equal to m, so let's say given h voters rather, what's the probability that exactly h of them are correct? Well, the first thing we have to do is we have to choose h of the voters to be correct. So how many ways can h out of n voters be correct? Well, that's going to be n choose h. So that's n factorial divided by h factorial times n minus h factorial. So this is just, however you do the calculations, it's just the total number of ways to choose h voters from among n total possible voters. And then you just multiply by the probability that those h voters are correct times the probability that the remaining n minus h voters are incorrect. So that probability is 1 minus p. So a concrete calculation will make this more explicit. What's the probability that at least 2 people are correct in a population of 3? Well, it's going to be the probability of exactly 2 people being correct plus the probability of everybody being correct. Well, the probability of everybody being correct is just going to be 2/3 raised to the 3rd power. So there's one way for everybody to be correct. And the probability of that is going to be 2/3 times 2/3 times 2/3. If we first choose 2 voters to be correct, that's going to be 3 choose 2, times the probability that those 2 voters are correct, which will be 2/3 times 2/3, times the probability that the remaining voter is incorrect. Doing the calculations, this is approximately 0.74. So it's 3 times 4 over 27 plus 1 times 8 over 27. If we increase the number of people, what is the probability that at least 3 people are correct in a population of 5? Well, it's going to be the probability that exactly 3 people are correct, plus the probability that exactly 4 people are correct, plus the probability that everybody is correct. And if we plug in the numbers, we'll see that the probability is actually increasing. So the probability goes up as we move from n equals 3 voters to n equals 5 voters. I'm keeping the size of the voters odd just for simplicity. What the Condorcet jury theorem tells us is that this probability is always going to increase. So here's the theorem. Suppose that the state of the world takes values 0 or 1. So this is what I mean by the proposition is either true or false. So there's some state of the world concerning the proposition at hand. It takes on 2 values, 0 or 1. And let's say r sub I is the event that voter I reports correctly. So our 2 assumptions are independence and competence. So independence just says the reports of the voters are independent, conditional on the state of the world. So the events R1, R2, ... are all independent given the proposition is either true or false, however it may be. Competence says for each voter, the probability that you report correctly has to be greater than 1/2. Then Condorcet noticed, this really follows almost directly from the law of large numbers, that if we suppose independence and competence, then as the group size increases, so as the number of voters increases, the probability that the majority opinion is correct increases, and in fact, it converges to 1. So almost surely, as the size gets larger, the probability that the majority is correct is going to be 1. Now, this generated quite a big literature. Many people noted that the independence assumption is rather strong. If you think about it, the situation that we typically find ourselves in, a group of voters get together and they chat about whether or not the proposition is true or false. And that, of course, is going to create some dependence among all of the reports. Well, the assumption of independence has been analyzed, and it's been explored about whether or not we can drop it and when we can drop that assumption and whatnot. I recommend this textbook presentation of the Condorcet jury theorem. It provides a very nice overview, very nice introduction to this very fascinating field.